Hi, I'm Natalie Parham, and in this video, I'm going to be talking about a work with my collaborator Adam Bene on unconditional quantum advantage for sampling with shallow quantum circuits. Adam is now at University of Calgary and I'm at Columbia, but we worked on this while we were both at the IQC. So what do we mean by shallow circuits? When I say shallow, I mean a circuit that is constant depth. Now, depth is the number of layers of gates required in the circuit. And I'll use the convention that inputs are coming into the circuit on the left and outputs are on the right. And in this talk, we'll only be considering circuits with bounded fan-in, bounded below a constant. So that means the number of wires coming into a gate is bounded by, say, 2. Also, I should note that all the circuits I'll draw in this talk will have gates only between nearest neighbor qubits, but that's out of convenience for that's out of convenience for drawing. In general, I don't require that a gate is acting only between neighboring qubits. Now, the circuit class NC0 are circuits that are classical circuits with constant depth and bounded fan-in. And QNC0 is the quantum version of this, so quantum circuits with constant depth and bounded fan-in. Now, at a first glance, it might seem like this QNC class would be strictly more powerful than NC0, or at least as powerful. But actually, this is a subtle point. And this is because NC0 has unbounded fan-out. At the end of any gate, as you can see this gate here, it can output, here it outputs it twice, it copies its output twice into 2 different gates, and here only once. But in general, a classical circuit can output it computes some function and then it can output as many copies of it as it wants, and copying is seen as being free. Whereas in the quantum setting, we aren't just able to copy qubits, we have this no cloning theorem, and this is reflected in the fact that in QNC0, there's also bounded fan out. And this is because the gates have to be unitary operations, so the number of input qubits equals the number of output qubits. And so bounded fan in implies bounded fan out. So this is why these two models are not obviously comparable. And in this talk, I'm going to investigate the difference between these two circuit models. Oh, I should move so you can see. Now, so now I'll talk about the power of these constant depth quantum circuits. So suppose you have a QNC0 circuit that takes input, an n-bit string as input. So I label it as the basis vector ket x, and it outputs some random variable that I denote as capital Q of x. So this is after you measure the output. So now it's a classical string drawn from some distribution. And the task is given x, sample from the output distribution Q of x. And now, how hard is this task? Well, a while ago, Terhal and DiVincenzo and Aronson combining their work, we can see that it's not possible classically to sample from this distribution in polynomial time. And this assumes that the polynomial hierarchy does not collapse to the 3rd level. So even though these are only constant depth circuits, we see already that it's not possible to classically simulate sampling from their output distributions. But this assumption here that the polynomial hierarchy doesn't collapse is why we call this a conditional statement. So it makes some assumption. This is a plausible assumption. It's standard in complexity theory, but nonetheless, we haven't outright proved that it's not possible. And so back in 2018, Bravi, Gossett, and Koenig investigated trying to prove a separation, or trying to prove that this is hard without making any assumptions. So they showed that if we, instead of considering polynomial time computation, we just consider this constant time computation. They show that with this constant time computation in NC0, you cannot simulate sampling from this output distribution. So now this is comparing more apples to apples because it's constant depth quantum versus constant depth classical, and they show a separation here. They actually show something even stronger. They show that just searching for an output y that has non-zero probability of being output is hard. And so in contrast to the previous statement about not being able to classically simulate it in polynomial time, this is an unconditional separation. And in their paper, Bravigas and Koenig also posed the question, can you still get a separation between NC0 and QNC0 if the circuit takes no input? So what do I mean by no input? So now the task is to sample from the distribution where the input is just all zeros. And a little bit more formally, they ask, does there exist a family of QNC0 circuits such that sampling from Q of 0 requires super constant depth classically? And in this work, we show that the answer is yes. So first, what many of you are probably thinking is, why doesn't this follow from the Bravigas and Koenig example? So we'll slow down for a minute and talk about the subtle differences between these two problems. So suppose that we have some hard-to-search circuit Q, and can we then use it to construct a hard-to-sample distribution? That doesn't take an input. And so, we have some circuit Q, and we know that, given X, it's hard to find some output, some non-zero probability output, Y. And so we could consider, okay, let's just think about the distribution where we give it a uniformly random input. So all qubits are set to the plus state. And so, X, so then the output distribution will be according to Q of X, where X is drawn to be uniformly random. And, we could also say that we're also going to output X. So you can consider the following distribution. It's just X, comma, Q of X. Where, X is uniformly random. And we know that given X, it's hard to simulate, given some X, like a worst case X, it's hard to sample from Q of X. But is this distribution still hard to sample from? And so this is asking the question, if some Y in the support is hard to find, does that mean that sampling from this is hard? But in fact, no such reduction like this can exist. And we have a nice example for why this is true. So the example that shows that you can't get this implication is the parity function. So we know that parity requires logarithmic depth to compute classically. And this is because if you have bounded fan-in, then you need logarithmic depth for the output to depend on all of the inputs. And the parity function does depend on all of the inputs. And the parity function is defined here. It's just the sum of the inputs mod 2. On the other hand, the distribution x comma parity x can be prepared in constant depth. So here is a naive way you might try to implement this. So you draw uniformly random bits, and then you compute their parity. So this construction will also require logarithmic depth. But there turns out to be something more clever you can do. And that is, you sample n uniformly random bits, but instead of just computing their parity, you compute a bunch of parities of 2 bits at a time. And each of these uniformly random bits that we prepare will appear twice, will be fed into 2 different parity computation, 2 different of these XOR, small XOR gates. And so if you add them all up, they cancel out, and it's easy to see that this is in fact sampling from our target distribution. And that it's also constant depth. It's only depth 1. And so here we see that sometimes it can be much easier to sample from the distribution than to compute the function in this case. And so this tells us that if you want an input-independent sampling separation, they are going to require techniques that are distinct from search separations. So the main result for this work, I'll first state it informally and then mention some caveats. So we show there exists some distribution over n-bit strings such that, 1, there exists QNC0 circuit that produces a distribution that's close to D. And secondly, that every NC0 circuit produces a distribution that's far from D. And the big caveat for this work is that, what do I mean by, sampling from this distribution? So the quantum circuit is given n qubits initialized to the all zero state, and then we measure the output, and then we care how close that is to the distribution. And the NC0 circuit, we give it uniformly random bits. And for this theorem, we limit the number of, the theorem only is proven if we limit the number of random inputs. So we can show that it's true for any delta, we have n plus n to the delta random bits as input. So as a direct comparison, this is fair because the quantum circuit has, n qubits and the classical circuit has a bit more. But, ideally you would like to get rid of this. You would like to take as many random bits as possible. And we'll talk more about some more recent work that improves this at the end of the talk. And so you could state this differently as the following corollary, that there exists a family of QNC0 circuits such that for each n, any NC0 circuit with limited random input bits samples from a distribution that's far away from the quantum circuit's distribution. And to make it a little bit more formal, when I say close and far, I mean within total variation distance 1/6 or greater than total variation distance 1/2 minus 1 over log n. And the corresponding distance is this one. So now I'll give a high-level proof overview. We start by proving a separation in a weaker regime. So we give ourselves help. We allow ourselves two things that are unreasonable. One is we're going to use some non-unitary gates. And the second thing we're going to do is we're going to give ourselves some advice, the GHZ state. And we're going to directly compare it still with the classical circuit. And we'll show a separation between these two, and then we're going to have to, slowly remove the help that we're giving ourselves from the quantum circuit and show that as we remove the assistance that we gave ourselves, the separation still holds. But what's really nice is when we give ourselves these two things, non-unitary gates, in this quantum advice state, then the separation is much cleaner to prove, and it's quite nice. And then, the more annoying work is getting rid of this help. So for each of the following regimes, we show that we can sample from a distribution that cannot be approximately sampled with an NC0 circuit, just to tie together this big picture. So, first we have the circuit with non-unitary gates and advice. And so we first show that approximately sampling from this distribution dA requires log n depth classically. But then we transform the circuit so that it's a unitary circuit. And then we show that the distributions are still close to each other. And the second thing we need to do is get rid of this GHZ state. And so what we do is we replace it with a poor man's GHZ state. And we show that, which can be prepared in constant depth. And now this one will change the output distribution. But we show in the second step that approximately sampling from this new distribution still requires log n depth classically. And finally, we need to do the same trick to convert the non-unitary part of the circuit to unitary and show that this doesn't change the distribution that much. And for the rest of this talk, I'm just going to focus on step 1, where we show how to construct the quantum circuit with advice. And so that corresponds to the following separation. We have a distribution that we can produce. We could approximately sample from this distribution with a quantum circuit when it's given this advice state, but every NC0 circuit cannot produce a distribution close. So how do we define this distribution? The distribution will have the following form, as we saw before. So the first n-1 bits are going to be uniformly random. And then the last bit will be some function of the first bits. And okay, my light in here is turned off, but I think you can still see me, so I'll continue. Anyways, so the last bit will be a function of the first n-1. And the function we consider might be a bit odd if you haven't seen it before, but it's this function where it's the majority mod p of x XORed with the parity of x. And the maj mod p, or majority mod p function, is just, it evaluates to 0 if the Hamming weight of the input x is, when you take it mod p, is at most p over 2, and it's 1 if it's greater than p over 2. So why do we use this distribution? Well, back in 2010, Viola showed that for some choices of p, the distribution of x comma majority mod p of x requires depth log n for a classical circuit. And we show that the same lower bound holds for this distribution dghz, which is just, we also add the parity to the last bit. And again, we still have both of these results, Viola's and ours, have this caveat that the fan-in is bounded and you have limited input bits to the classical circuit. So how do we construct our quantum circuit? Again, I remind you again that it's going to be a non-unitary circuit, and we'll show that this is close to the target distribution, and then we'll convert it to unitary. So our non-unitary circuit will consist of the following non-unitary gate. So it looks like the poly X rotation gate, but we're going to control it on ourself. So what does this do? This has the effect of mapping 0 to itself, but then 1 will sort of activate the poly X rotation gate, and it gets sent to a combination of 0 and 1, as if, we rotated it by angle theta. And it's easy to see that these two states are not orthogonal. So clearly this gate is not unitary, but it's still a linear map. And we're going to put it into our circuit and just consider it as a matrix in a circuit. That's still a well-defined mathematical object. And we're actually going to be most frequently using the adjoint of this gate. So that means that it has the following. We can simplify the circuit diagrams as follows. If you post-select the output on 0, then this is equivalent to just the 0 state. And if you post-select on 1, then this is like, you had applied the gate. And so measuring the output in the computational basis tells us whether the gate was applied, the rotation gate was applied. And so now I'll show you how it's easy to get close to our target distribution just using these gates in our advice state. So first, I want to consider the state that's the even state, which is uniformly random over all even weight bit strings. And we can prepare this state by just applying Hadamard gates to the GHZ state. And I want to claim that this circuit produces a distribution that's close to our target distribution. So we just need to show that, suppose we measure the first n-1 qubits and we get the following measurement outcome, x1 through xn-1. And we need to show, one, that this is sampled according to the uniform distribution, and that if we measure the last bit, that it's, with high probability, it's going to equal majority mod p plus parity. And so now let's analyze this circuit. Because if we measure the last qubit, this tells us whether or not the rotation gate was applied. So we can just write these rotation gates like this. And now note that if you add a poly X to any qubit of the even state, say you flip the first qubit of the even state, now this maps it to the odd state. And it didn't matter which qubit you flipped. So you could have assumed you just flipped the last one. And this is also true for the poly X rotation, how it acts on the even state. It has the same action whether or not you apply it to the first qubit or the last qubit. So we can push all of these rotation gates down to the last wire. Like so. And then also now we can add up all of the x1 through xn to, we can rewrite the gate like this. So now, the number of times we apply the rotation gate scales with the total Hamming weight. And one way to prepare the even state is by first preparing the uniform superposition on the first n-1 things, and then computing the parity into the last qubit. And so we could equivalently just write the following. So we have the last qubit starts as the parity. So yeah, we get the first n-1 are random, and then the last one is the parity of it. And so we set our parameters to the following things. And so then what happens? So we know that X is uniformly random. That's good. That's what we wanted. And the second thing we know now is that if we measure Y, it equals parity with probability cosine squared of pi over p times the Hamming weight minus pi over 4. And that's because, this that's the probability that this rotation, that's the weight that this probability, sorry, the weight that this rotation gate has on identity versus X is cosine of this angle. And so all that's left is to show that Y equals major mod plus parity with high probability. And it's not plotting this distribution of the probability that Y equals parity shows us that in fact this is correlated with the function that we want. So, on the left-hand side, I've written the probability that Y equals parity in this black line. And you can see that this is anti-correlated with the major mod function. And so, on the right-hand side, we see the probability that Y does not equal the major mod plus the parity is always bounded below 1/2. And so we see that Y is correlated with our target function. Okay, so we've shown already that we can sample from a distribution close to the target one. But now we need to show how to convert this to a unitary circuit. So what we do is we block these non-unitary gates into blocks of size m. And so it's like, because we could move, post-selecting on some output being 1 or 0, it tells us whether or not a gate was applied, and it doesn't matter where we applied the gate. So the way in which this state is affected by the circuit doesn't change if we control, instead of self-controlling, we control on the wire above it. And so we can do the following. We can do these cyclic control gates. And it's still not unitary. But we're going to consider this block of gates. And we call it A sub m theta. And we show that there exists some unitary that approximates A sub m theta, and the approximation gets better as m increases. And so, then the total error of the whole circuit will scale like the following. And this ends up being 1 over, at most 1 over n if we set m to be sufficiently large, but still a constant. And so yeah, setting m to be still a constant, then these unitaries are only on a constant number of qubits, so they can also be implemented in constant depth. And now I don't have enough time to get into the classical lower bound too much, but I'll just give a taste of what sort of insight is used for these. So we use the framework we extend the framework from Viola's paper 2010. And we know that for every NC0 circuit, every output bit is a function of only a constant number of inputs. So in particular, we can find independent blocks of the output that have some that are independent, meaning there's some input that for each block there's some input that only influences that subset of the outputs. So we can find, like, we can group some colors. So we have the orange, green, and yellow ones, and we're just going to fix all we can fix all the other inputs, but we can always find a subset of inputs where we can always find a subset of inputs where if we fix all the other ones, we can sort of turn on and off these colored ones, and they will independently influence different blocks of the output. And suppose without loss of generality that the last bit of the output is not in one of the blocks. So that means that this last bit, f of x, should be fixed. But so yeah, f of x is fixed, but still x will consist of many independent blocks, and that shouldn't be possible. So if it should, for our function, where we consider the parity x, if we flip one of the bits of x, it should be also flipping f of x with high probability. And so here you get a contradiction. And to summarize, here I have this slide again about how the proof worked. We start with the non-unitary gates and the advice, and we separately have to use techniques to transform to unitary and to remove the GHZ state, which I didn't talk about in this talk. And now I'll just briefly mention some open questions. So the first is that it'd be nice to have some verification or certification algorithm. So we know that this is we know that this is a separation, but in fact, being able to tell, so I want to tell, do I have a quantum circuit or a classical circuit? And I know it's constant depth for some reason, but I don't know if it's quantum or classical. It's actually computationally, it's really actually not computationally easy to tell if you're sampling from the right distribution. And so this particular distribution, it's not you can't do an efficient verification or certification of if you're sampling from it correctly. And then another thing you could do is try to get stronger classical lower bounds, like for the AC0 circuit class. There's been other lower bounds against AC0 for sampling by Viola in different papers. And also, can we get rid of the requirement on the number of random input bits to the classical circuit? And can we use a finite gate set for the quantum algorithm? So our quantum circuit doesn't use gates from a finite gate set. And I'll note that these 2 points that I've highlighted in blue have recently been resolved by Greer, Kane, Morris, Ostuni, and Wu, where they showed for a different distribution that they get a separation that does get rid of reach these 2 points that our work didn't. And they're also, I believe that Anthony will be giving the talk. I'm not 100% sure, but there should be another recording and another talk at ITCS for that paper. And finally, for our distribution, can you get an explicit circuit construction for this unitary U sub m of theta? We show how you can compile it, but not necessarily from a finite gate set. And that's all for this talk. Thank you for watching, and I hope that my floating head didn't block anything. But thanks for watching. If you have any questions, feel free to email me and Adam.